Hello YouTube! Today we're going to be launching into the first of our three sort of ways that the forces unit can get a lot harder. So if you're not particularly comfortable in the stuff from before, today is not going to be a good one. I would pretty strongly recommend making sure that you're all squared away on that before this, because we're going to be using all the stuff from the last few, but then making it harder. So ideally, end of the day, you should be able to. Sorry, one sec. Whatever. You should be, ideally by the end of the day, be able to use the coefficient of friction to model how something's going to move, especially when there's friction on the object. Big parts of that are going to be able to label friction on the free body diagram, which is something we've pretty much already been doing. Define the coefficient of friction and know what that is, and then actually use the system of equations that you'll generate with the friction equations in order to solve everything out. So in particular, a few more details on friction than we've given so far are basically that friction is something that tries to stop objects from sliding against each other. And the way that that'll work is that it's always going to be parallel to the surfaces. So like if the surfaces are like this and it's sliding like that, if it's trying to slide this way, friction will go that way. If it's trying to slide this way, friction will go that way. But if it's a vertical surface, friction could be vertical as well. So if you're trying to slide up a wall, friction will go down. If you're trying to slide down a wall, friction will go up. And that works no matter which way the surface goes. It's based on the way it's trying to slide. And I think more accurately, if it's not moving, it will go in the direction that makes that happen. So it'll go whichever way it needs to make forces balance, basically. There's a little more nuance that happens if you've got like a surface that has something else on it. So like if my water bottle is on my hand and I move it side to side, there is friction that is stopping the two things from sliding against each other. And that's actually the thing that makes it speed up, move to this side, speed up, gain a velocity in this direction. And then it just keeps the velocity without anything, because that's how Newton's first law works. And then as it slows down, friction is what slows it down and causes it to stop, even though the surfaces aren't rubbing against each other. It's that attempt of rubbing against each other and the failure to do so because of friction that causes it to move. But that's probably not a situation you'll have to deal with. What friction is actually being caused by is that all these little objects have these tiny little bumps and grooves and imperfections on them. And those bumps and grooves and imperfections are going to slot into each other. And so you'll get something like this, where some of them are pushing against each other, trying to stop that from sliding. And that's really all that causes friction. So if you want to make that so that you have a more difficult time getting those things to rub against each other, squishing them into each other harder is going to make there be more friction. What's the force that happens when you try to smush two things into each other called? Well, normal force. So this is actually just directly saying that the more normal force you have, the more friction you'll have. Additionally, the rougher the two surfaces are, meaning the bumpier they are, the more friction you'll have for the same amount of normal force. There's one other thing that's a little weird, which is that for a stationary object, there's two different types of friction, one of which happens when the objects aren't sliding against each other, one of which happens when they are sliding against each other. And it turns out that you can get more friction if they're not sliding against each other. And the way that I kind of think of that is like a jet ski on waves, or like something skipping across waves, where you don't go all the way down into the bottom if you're moving really quickly. You just kind of bounce off and move on to the next one. Whereas all those grooves have time to sort of settle into each other and get nice and cozy, which makes it much harder to bring it up and over all of the grooves when they're not moving. So, this is the first equation for kinetic friction. And kinetic friction, kinetic meaning moving, is something that's going to come up a couple times in this class. It's only going to happen when the two objects are actually sliding against each other. And this one is actually a lot easier, specifically because there is an equality. There is an equality sign, meaning that they will always be mu k times Fn. Now, what's force of friction? Well, force of friction is Ff is force of friction, which is measured in newtons. Mu, that's what that symbol is. If I'm being really good about it, which I will probably with my handwriting and less so with a computer mouse, it's hard to see here. I like putting a little loop in it so that I know that it is definitely not a U and it's definitely not an M. Otherwise, it looks a lot like an M. But this is a Greek letter. It's pronounced mu. And that's your coefficient of friction. If it's got a K after it, it's the coefficient of kinetic friction. If it's got an S after it, which is the next one we'll learn about, it's a coefficient of static friction. In particular, what this is literally just a thing that's the property of the two objects. So anytime you have any two surfaces, those two surfaces combined with each other will have a coefficient of static friction and a coefficient of kinetic friction. There isn't really a way to find it other than by doing some experiments on it. So if you have a problem, they'll either be asking you to use the math, but using this equation to figure out what your coefficient of this equation to figure out what your coefficient of static friction is, or kinetic friction, or they'll give it to you. It is rarely going to be bigger than 1. Most of the time it'll be a fraction. Just because that would mean that you're getting more force out of it than you're putting into it, which is technically not what is actually happening, but like typically speaking, coefficient of friction is smaller than 1. And Fn is normal force, so the same forces we've been calculating for the last few units, or days. So, as an example, how much normal force is required for a 30 kilogram block to slide down a wall at a constant 20 meters per second if the coefficient of kinetic friction is 0.3. So let's start drawing something out for this problem. We've got a block and it is sliding against a wall. Now, we need some normal force here. Well, the only contact surface that this has is the walls. Normal force is always perpendicular to that. So my normal force is actually going to be going this way. Gravity will be going down. If the block is trying to slide down the wall and actually is sliding down the wall, then friction will be going up the wall. This currently would be flying off of the wall, or accelerating away from the wall, which is probably not happening. So there's probably a force like a person pushing it in as well, and I'm going to call that force 1. So what we're looking for is Fn if our acceleration is 0. Now, why do I say my acceleration is 0? Well, it says it's sliding at a constant 20 meters per second. Constant velocity means no acceleration. So let's hop to it, which is my phrase of the day, I guess. So taking this and turning it into a free body diagram, I do already have most of it done, but just being a little careful, making sure I've got the dot. We've got mg here, we've got F1, we've got the normal force, and I'm going to be a little more careful labeling friction. It is the force of kinetic friction. So just like before, we're going to do our setup for the x, we're going to do our setup for the y. It's just that when you have friction involved, you'll have a third equation, which is whichever friction equation winds up being relevant. So in the y direction, we've got our force of kinetic friction and gravity. Gravity is going down, so I'll make it negative. This is equal to my net force in the y direction, and that'll be equal to MAY. And the force of kinetic friction is going up, so I'll make it positive. That'll need to equal mass times acceleration in the y direction. In my x direction, I've got that my normal force, net force in the x direction will need to equal mass times acceleration in the x direction. Now, both of these accelerations are going to be 0 because it's moving at a constant velocity, meaning there's no acceleration. Additionally, I can go ahead and plug in for here, we've got normal force going backwards, so minus Fn, plus force 1, whatever that is, going forward, and that'll need to equal to 0. The problem is I don't know what F1 is, so I can't use this equation to figure out normal force unless I can figure out F1. So let's see if there's another equation with normal force. Well, we did just learn one, which is that our force of kinetic friction will be equal to the coefficient of kinetic friction times normal force. If I know the force of friction, this surface has a coefficient of friction given as 0.3. And while I'm here, I should have copied this down earlier. This is a 30 kilogram block. And so if I can figure out the force of friction, I know that this is 0.3, and I'd be good to go. So I'm going to need a way to find this in order to get the normal force of the thing I'm looking for. Well, let's look for another equation that uses it. Right over here, we've got force of friction. So this equation would work if I know mg, which I do, and I know acceleration, which I do. So let's use that. Looking in our y direction again, we've got that the force of kinetic friction minus mg will need to equal 0 here. So all I have to do is add mg to both sides, and I'm done. In this case, we've got 30 kilos, and g is always 10. So that gives us out 300 newtons. So our force of friction needs to be 300 newtons big. So in order to get our force of friction to be 300 newtons big, what we can do is take that, plug it in over here, and find out what our normal force would need to be. So we can do force of kinetic friction equals mu times Fn. We just have to divide each side by the mu, and we've solved for Fn. So our normal force is equal to force of kinetic friction divided by mu k, which is 300 divided by 0.3, which is 900 over... Nope. Hang on. Boop. Boop. So 1,000. So our normal force for this one is going to need to be 1,000 newtons pointed away from the wall. All right, so that's the first type of friction. Second type of friction I want to talk about is if they're not sliding against each other. So in particular, if you're given a static coefficient of friction for a problem and you're given a kinetic coefficient of friction for a problem, the way you pick between the two of them is that static means not moving, kinetic means moving. The one thing that gets weird about static is that it is not an equal sign. Kinetic friction will always be the same because if it's moving, it can always be getting slowed down if the friction's too big. The thing about static friction is if static friction was always the same, then that gets really weird. Because if I have this water bottle and I just barely push it a little bit, it's not going to accelerate. And the reason it's not going to accelerate is because the friction is balancing out the other force of me pushing the water bottle. If I push harder, friction will have to do more work to stop it from accelerating, so friction will have to become a larger force. Eventually, if I keep pushing it, it'll start to slide. If the force of static friction was always the same amount, when I pushed this a little, it would be pushing back with that same amount that was as big as it could possibly be, and this thing would start sliding backwards into my hand, which isn't what happens. So in particular, just like how normal force is however big it needs to be, static friction is however big it needs to be to stop things from sliding and make the situation actually work. There is a little bit of an exception to that, though, because static friction has a limit. So what the equation for static friction is telling you is how big it can get before static friction stops working. That equation is mu Fn. So instead of the kinetic one where it's like this is how big friction always is, what this tells you for static friction is friction could be up to this big. If the amount of forces that are fighting against the friction are bigger than this maximum value, which is what the equation tells you, then the object will slide and you'll have kinetic friction instead of static. But if the amount of force that's pushing against it is smaller than this, friction will just make it balance out and nothing will happen. So again, mu is the coefficient of friction. In this case, the S tells you that it's static. Typically, this is bigger than for kinetic. Fn is normal force. And in all bold, all caps or whatever, this thing is not always going to be the size of the friction. It's telling you as big as it could possibly be. Usually it'll just make it balance the same way that normal force does. Or I guess make the situation work the same way that normal force does. Normal force can actually make something unbalanced if, for example, you're like having an elevator. So someone tries to push a 110 kilogram couch initially at rest with a 5,000 Newton force. Right. With a 5,000 Newton force at an angle of 57 degrees to the right of the vertical. If the coefficient of kinetic friction for the surface is 0.4 and the coefficient of static friction is 0.6, what is the acceleration of the couch? So the reason this question is framed as weird as it is will become relevant eventually, but to start with, let's just get a picture down. All right. So we've got our object. We know that it's 110 kilos. We know that we've got a 500 Newton force that is 57 degrees to the right of the vertical. And we know that for the surface, mu k is 0.4 and mu s is 0.6. So the question is asking what the acceleration is, and we've got a couple different ways we could think about this. The first of which is to just sort of dive right in, start doing all the calculations that we were doing last time and not really worry about it and hope we're fine. I'd rather take it a little slower and make sure we get this stuff right. So to do that, let's think about the difference between the static friction and the kinetic friction. The kinetic friction is if it starts sliding, that'll be the one we use. The static friction is telling us that it can go up to a certain amount to stop it from sliding. So the way that'll be relevant here is that we can figure out, do we have enough static friction available that the static friction will just balance out and it won't start sliding? Because if we're pushing harder than the static friction can go, it'll start sliding and we'd have to calculate it using kinetic. If we're not pushing hard enough, it won't start sliding and the acceleration will be 0. So let's figure out what our threshold for static friction is and then go from there. Well, the force of static friction maximum is equal to mu times Fn. So I'm going to need Fn if I want to find the force of static friction. So for that, we're going to draw a free-body diagram. Well, we've got this force going at this angle. We've got the normal force going straight up. We've got gravity going down. And we'll have friction going the opposite direction along the floor. I'll set up my y equation because that one works. My net force in my y direction is equal to mass times acceleration in the y direction. Now, I'm hopefully not lifting this couch off the ground. I don't think that's going to be happening. And as a quick double check, gravity is greater than 1,000, and the normal the force that I'm pulling with is 500. So there's no possible way that I'm lifting the couch off of the ground. So let's go ahead and set up our free body diagram specifically with our components so that we can set up our equation. So we've got our y component going up. We have our x component going to the right. And because this, the force of my person, is 500 newtons, breaking it up into components, we'll have Fpx is equal to 500 times the cosine of 57, which is going to be the big one. So that's should be 400, but let's double check. 500 cosine 57 equals that should be 53 degrees. That should be 53 degrees, so it's actually a whole number. I'm going to change that, actually, just because I don't want to deal with the decimals. All right, great. 300. And this should be sine because it's opposite. What a day. What a time to be alive. All right, 500 sine 57 will give us 400. Coming over here, because this one is next to the angle, this will be Fy, which will be, and that's the force person in the y direction, 500 times the cosine of 53. Because of that, we wind up with 300 newtons, which is that one right there. So in our y direction, we've got our normal force going up, so positive, our force from the person in the y direction going up, so positive, and mg going down, so negative. Now that all needs to balance out, elsewise the couch would be either being lifted up or going through the ground. Great, so we can solve for our normal force this way, and then once we've got our normal force, we can figure out what our maximum force of static friction is. To do that, all we got to do is subtract off the force of the person in the y direction, which we know, and add over mg, which we also know. And that leaves us with the normal force equals negative force of the person in the y direction plus mg equals, plugging in our numbers, 3 hundo and 1,110 for 10 times 110, which gives us 800 newtons. So we have 800 newtons of normal force. What we can do is take this 800 newtons of normal force and plug that in to this equation to get our force of static friction. In doing that, we've got our coefficient of static friction as 0.6. Again, we're checking if it doesn't move, so we're using static. We've got our normal force of 800, and 0.6 times 800 is 480. So what this tells us is that static friction can go up to 480. So what we need to figure out is, are we pushing it hard enough to go over that? If we look at the force that's fighting against friction in the x direction, it's this 400 newtons. If we're only pushing it with 400 newtons, then friction can be big enough to match that. So what'll happen in this case is we'll have our 400 newtons going to the right. This can go up to 480, but instead it'll go up to 400 to make it balance out. If we were pushing with 500 newtons to the right, all of a sudden this thing would start accelerating because we had pushed harder than it could stop, and we would start sliding and we'd have to use kinetic friction. But because it's able to balance out, because the force that we're pushing it with is small enough, it doesn't accelerate. So our final answer for this one is that our acceleration is going to be equal to 0, specifically because we're not pushing it hard enough to overcome this 480. So before we wrap up, do you want to just talk about a couple tips that'll wind up being pretty relevant? Just in general, if you're trying to pick between kinetic versus static, moving means kinetic. If it's moving at a constant velocity, you use kinetic, and because it says that constant velocity thing, make sure you have your forces be balanced out. If the object is not moving, there are two big options. The first one is that either the forces are balanced and you're not going to have to use the friction equation, because it's just how friction is however big it needs to be to make it balanced, just like it was before you learned the friction equation. Or if the forces are balanced and you do need to use the friction equation, one way that could happen is you want to think of it as, or if you look at the text, it'll say something along the lines of, how much could you push it before it starts to move? Find that maximum amount and say if you push it literally any more than this, it'll happen. The other one is if the problem says it's using the maximum static friction, use that equation, use it as an equal sign, do the maximum thing. The other way is to check whether or not it starts moving. And that'll be like for the example problem we just did, where you take however big friction could be, you see whether or not the forces that are pushing to try to get it to happen are bigger than that, and if they're not, it doesn't start moving. So, thanks, and goodbye, YouTube.